Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics, lecture number 19. Before I start this lecture, let's review what we have done in the last lecture. In last lecture, we studied Sturm-Liouville problems. We started this topic 2-3 lectures ago, and we continued in the last lecture with the same topic. And then we went on to study the properties of regular Sturm-Liouville problem. And then we saw a few examples as well. So we actually solved 3 examples last time, SL problems with the different boundary conditions. We discussed 3 cases in each time, in each example, lambda negative, positive, and equal to 0, and we saw that we got different eigenvalues and eigenfunctions. Today we will be starting a new topic, which is Laplace transformation. So this is an integral transform which is very helpful in solving both differential and integral equations. So we will briefly discuss what Laplace transform is, and then we will find out the Laplace transform of some elementary functions, and then we will study the properties of Laplace transform. So let's start today's lecture with Laplace transform. Laplace transform is essentially a mathematical tool which can be used to solve several problems in science and engineering. This transform was first introduced by Laplace in the year 1790. What is the definition of Laplace transform? If ft is a continuous function and simple valued function of the real variable t defined for all t between 0 to infinity and is of exponential order, then the Laplace transform of ft is denoted by capital Fs and is defined as this integration, that you multiply ft by e to the negative st and then you integrate it from 0 to infinity. So we are integrating with respect to t, so of course this is a function of s. See, e to the negative st, so s is another variable here. So there is this notation as well, L for Laplace, Laplace transform of ft, and it is converted this t to s. So new parameter is s here. So this notation LFTS means you have transformed a function of t to a function of s, and we denote it by capital F as well. Now over the range of the values of s where the integral exists, for whatever s this integral exists, that will be the domain of our new function. Here s is a parameter, real or complex, it can be anything. Remark, if ft is piecewise continuous in the range t positive and is of exponential order gamma, then the Laplace transform LFT exists for all s greater than gamma. Alright? So if it is a piecewise continuous, even if it is piecewise continuous, your Laplace transform will exist for s greater than gamma, where exponential order of f is gamma. From the definition of Laplace transformation, LFTS is equal to this. We just define Laplace transform like this, alright? So now if it is piecewise continuous, not continuous, so there may be a discontinuity at capital T. Let's say at capital T it has a discontinuity. So you can break your integral from 0 to t and from t to infinity. Alright? Since ft is piecewise continuous and every finite interval from 0 to t, I1 exists, whereas I2, it is continuous from 0 to t, so we have no problem. We can integrate it from 0 to t. Now from t to infinity, what we can do is for this second integral I2, I can take the bound on this. I2 mod should be less than or equal to the mod of the integral. You know that mod of this whole integration is less than or equal to integration of the absolute value of the function. Means if you bring the absolute value inside, it is not exactly equal. It will be less than or equal to the inside thing. But ft is a function of exponential order. What do we mean by exponential order? That ft is less than or equal to m e to the gamma t. M e to the gamma t. If you can write any function like this, then it means your function is of exponential order gamma. Alright? So it means your ft is, if I replace this ft by m e to the gamma t, I will have another inequality, less than or equal to replace ft by e to the gamma t. So you will get e to the minus gamma t dt. And of course now you can integrate it very easily. Alright? So if you integrate, you will get e to the minus s minus gamma t divided by s minus gamma. And this is of course true for s greater than gamma. In other words, I2 can be made as small as we like, provided t is large enough, and therefore I2 exists. Because of course if it is bounded by this thing, alright, then it means I2 exists. Hence LFTS exists for s greater than gamma. Alright, so this is fine automatically, and this is also bounded integration. If it is bounded, it will converge, of course. So your Laplace transform exists for s greater than gamma. If s is less than gamma, you see this will become e to the plus sign. If s is less than gamma, this is negative, negative, positive. So it means this can become larger and larger. So you cannot say that it is bounded. But if e to the power is negative t, then of course it will come in the denominator. Now if t is large, this whole thing will be very small. If this is very small, I2 is bounded automatically. Alright, so these were a couple of remarks here with proofs. So let's find out Laplace transformation of some elementary functions. That if ft is x or 1 or exponential, these type of sine, cosine. So what will be the Laplace transform of these elementary functions? Let's find out some Laplace transform of some elementary functions. Let's say 0, 1, t, e to the at, e to the minus at, cosine, sine, cosine hyperbolic, sine hyperbolic. So let's do few of them. I will do some of them, and I'll leave some of them for you guys with the same steps. You can prove the other things as well. Laplace transforms. In short, sometimes we call it LT, Laplace transforms. So what we said is let's find Laplace transform of 1. Alright, what will be that? 0 to infinity, 1 e to the minus st dt. Right? Limit m goes to infinity, 0 to m, and e to the minus st dt. E to the minus st divided by minus s, 0 to m, that is limit m goes to infinity, e to the minus sm over minus s, and minus e to the 0 over minus s. Alright, so this is limit m goes to infinity, 1 minus 1 over s e to the sm, and this is plus e to the 0 is 1 over s. So now if s is positive, then m goes to infinity will make this thing go to 0. But if s is negative, then this will come up here. If s is negative, then this is positive m. So if m goes to infinity, this will go to infinity. So the right hand side exists, and the limit is 0 plus 1 over s if s is positive. So for only positive values of s, this will happen. So your Laplace transform of 1 is 1 over s, and it is defined for positive values of s. So this is the Laplace transform of 1. let's say what is the Laplace transform of e to the at, e to the at, let's say exponentials. So that is e to the at, e to the minus st dt, again replacing infinity by m and letting m go to infinity. This is a minus s t dt. So e to the minus a minus s t has the integration e to the a minus s t divided by a minus s, and this is from 0 to m. Now if you replace m, it is e to the a minus s m over a minus s, and minus e to the 0 is 1 over a minus s. So now a to the power a minus s m again depends on a and s. If a is less than s, it is negative, so it will come down and it will go to 0. If a is greater than s, then it will remain up here on top, and m goes to infinity, will make it infinity. So this is 0 if a is less than s or s is greater than a. Alright, so if s is greater than a, this will be negative. So negative e to the negative m, m goes to infinity, will go to 0. Alright, so this will become 1 over s minus a if s is positive. So this will be the domain. Now it's not s greater than 0, it's s greater than a. So this is defined for s greater than a. So the Laplace transform of e to the at with respect to s is 1 over s minus a. So what will be the Laplace transform of e to the 2t? It will be 1 over s minus 2. E to the 3t, 1 over s minus 3. E to the minus 2t will be 1 over s plus 2, right? So similarly you can do other things. Now let's find out the sine and cosine transform of sine and cosine. Alright, so Laplace transform of sine and cosine, let's say sine at s and Laplace transform of cosine at s. Let's find out these two transforms. These two transforms can be obtained by, if you recall, Euler's formula is e to the iota theta is cosine theta plus iota sine theta. So if I find the Laplace transform of this thing, I will get the Laplace transform of these two simultaneously. Alright? And if you want to calculate it separately, that's fine as well. So Laplace transform of e to the iota at is equal to 1 over s minus iota a, right? Just from here, it's iota at, so I said s minus iota a. Alright, so now s minus iota a is complex. So if you multiply and divide by s plus iota a and s plus iota a, what you will get is s plus iota a divided by s square minus iota square a square will make it plus s square plus a square. So that is s over s square plus a square plus iota a over s square plus a square. Now cosine is the real part of this e to the iota at, so this will be the transform of cosine and this will be the transform of sine. Now since cosine at is the real part of e to the iota at and sine at is imaginary part of e to the iota at, so therefore Laplace transform of cosine at s will be the real part of Laplace transform of e to the iota at s, and we just saw that this is s over s square plus a square. Real part is with terms without iota, this one, right? And this term without with iota, so this is imaginary part. So Laplace transform of sine at s is imaginary part of Laplace transform of e to the iota at s. So that is a over s square plus a square. So I got Laplace transform of cosine and sine together. You can do it directly as well. You can do it directly as well by integrating cosine at. If you do it directly, what will happen that you need to multiply cosine at by ft by e to the minus st and integrate by parts twice. If you integrate it by parts twice, you will get your answer like this. But that will be a lengthy procedure. This is the shorter version. So similarly, you can find the Laplace transform of cosine hyperbolic and sine hyperbolic as well. So Laplace of cosine hyperbolic a t s is Laplace transform of cosine hyperbolic a t is e to the a t plus e to the negative a t divided by 2. And Laplace transform is linear because it's integration. Integration is a linear operator. So you can say that this is 1 by 2 Laplace transform of e to the ats and plus 1 by 2 Laplace transform of e to the minus ats. Right? This is linear, so you can distribute it like this. So we know Laplace transform of e to the at is s minus a, and we know that if a is negative a, so this will become s plus a. Right? For negative at, it will become 1 plus a because a becomes negative a. So if a is negative a here, it will become s plus a. Now you can take the LCM s minus a, s plus a. You will get s plus a plus s minus a. So it's gone. You got 2s by 2, so it's s over s square minus a square. So you see the only difference is cosine at has s over s square plus a square. Cosine hyperbolic has s square minus a square. And similarly, you can verify that Laplace transform of sine hyperbolic at s is a over s square minus a square. Alright, so you can verify it. It's very easy. Alright, so similarly, you can find the Laplace transformations of other functions as well. The important is t square, tn. Alright, so let's find Laplace transform of tn. This is important because this will take care of many functions, many polynomials as well. Alright, 0 to infinity tn e to the minus st dt. So here we can do it by integration by parts, that tn as it is e to the minus st by minus s from 0 to infinity minus 0 to infinity. The derivative of t is n tn minus 1 and e to the minus st by minus s dt. Now again, if s is positive, this will become 0 because as t goes to infinity, this will be 0. Alright, and at 0 it is 1, but at 0 this t will be 0 because these are the limits for t 0 and t goes to infinity. Right? So of course at 0 this will be 0, at infinity this will become 0. Here you can say that this t to the power n goes to infinity and e to the minus st is 0. So you can use L'Hopital rule if you want. Alright, you have limit t goes to infinity tn by e to the st. There is 1 over s as well if you want to write. Okay, minus 1 over s. And at 0 it is 0, so I am not writing that. Minus minus plus, this is n over s, the 0 to infinity, tn minus 1 e to the minus st dt. Here, if you use L'Hopital rule, this limit is the same as the derivative of top and the derivative of bottom. You know that e to the st will have the derivative e to the st, so this is not going anywhere. After n derivatives, this will be still e to the st, and after n derivative, this will become constant. So again, constant divided by e to the st as t goes to infinity will make it 0. All right, so this is 0 by L'Hopital rule or L'Hopital rule. All right, so this is 0. So this is n by s, 0 to infinity. Now if you look at this integration, this is the Laplace transform of Tn minus 1 s, right? So what we have proved here is that if we want to take the Laplace transform of Tn, this will give you n over s times Laplace transform of Tn minus 1 s. Now using the same relationship, if I want to write the Laplace transform of this thing, n minus 1, it will be n minus 1 over s and Laplace transform of Tn minus 2s, right? And similarly, if I write Laplace transform of this thing, this is n minus 2 over s times Laplace transform of Tn minus 3s. All right. Similarly, Laplace transform of this is n minus 3 over s times Laplace transform of Tn minus 4 s, and so on. You can continue with that. So it means that Laplace transform of Tns is n times n minus 1 times n minus 2, so on, divided by s square, cube, 4, right? N has 1 power, n minus 1 has 2 powers, and so on. So where we will stop? We will stop at Laplace transform of, let's say, at the end, when n minus n, this will become 1, right? So this will become Laplace transform of 1 eventually somewhere. When, if I expand it n times, I'll get 1. So when you had 3 outside, you have 4. So when you have 3 times 2 times 1, then your t to the power 0 will occur, because there is 1 less outside. If this is 3, then this is 4. If this is 4, this is 5. All right. So if t to the power 0, then you have 1 outside. And how many n's? You have s to the power n, right? You have s to the power n. Is it s to the power n? Because you have 1 s over every factor. N has 1 factor, n minus 1 has n factor, s factor. So each factor upside has s factor. There are n factors here, 1, 2, 3 up to n. So that's why s to the power n will occur. And we just know that, we just proved few slides back that Laplace transform of 1 is 1 over s. All right. So s is positive, we know that. And we know this from beginning here as well. This is 0 by L'Hopital rule, and when s is positive. So it's already true that this is true for s is positive. All right. So it means your Laplace transform of Tn, s is n factorial over s n plus 1. You see there are Sn and 1s comes from here. So Sn plus 1, and this is n factorial. This is n factorial. All right. So you got this thing. Or you can write it as gamma function. Gamma function n plus 1 over Sn plus 1. Now, why we write gamma function? Because it's easy to remember that this both has n plus 1, n plus 1. But n plus 1 gamma function means n factorial, exactly. All right, and this is true for us. So we got a lot of transforms now, right? We have Laplace transform of 1, of e to the at, of sine, of cosine, of sine hyperbolic, of cosine hyperbolic, of Tn. Tn takes care of many, t, t square, t cube, and all the polynomials. All right. What will be the Laplace transform of 0? We did not cover this. What will be the Laplace transform of 0? 0 to infinity, 0 times e to the minus st dt is equal to 0 dt Integral of 0 is constant. So constant from 0 to infinity is 0. So Laplace transform of 0 is 0. Alright? So similarly you can prove other functions as well. So now we know the Laplace transform of 0, 1, t, e to the at, e to the minus at, and all these functions. I intended to do only few of them, but I think I have done all of these transforms for you guys. So just make a table of these transforms. I did this example as well, t to the n. This is not square root, this is gamma function. This is not a square root, it's a gamma function of n plus 1. Sometimes people write gamma function over the whole n plus 1 like this, gamma n plus 1. So this is not square root, it's a typing mistake. Properties of Laplace transformations. I have used this property, linearity property. When I proved the Laplace transform of cosine hyperbolic at, I said Laplace transform is linear because integration is linear, so I can distribute this Laplace transform over the sum, and the constant multiples can be brought out. So this is clearly a linear operator. If C1 and C2 are any two constants, F1s, F2s are the Laplace transforms of F1 and F2 respectively, then the Laplace transform of LC1 F1 plus C2 F2 is equal to C1 Laplace transform of F1 plus C2 Laplace transform of F2. It means it is C1 capital F1 plus C2 capital F2. I use this property. By using these properties, we can find out the Laplace transform of additions and scalar multiplications as well. So will it be hard for you to find Laplace transform of sin at plus cos bt? It's very easy. What is the Laplace transform of sin at? It is 1 over a over s square minus a square. Cos bt is s over s square plus b square. Alright? So you can clearly add their Laplace transforms to get the Laplace transform of this whole function. Similarly here, these all are very, very easy tasks. You can we have Laplace transform of each one of them. Sin at, cos bt, t, cos t. So you just have to add their Laplace transforms to get the answers. Shifting property, this is an important property. If a function is multiplied by some exponential e to the at, the transformation of the resultant is obtained by replacing s by s minus a. So what you did is basically you shift the origin. S function has origin at 0, but s minus a has origin at a, because at s is equal to a, s minus a becomes 0. So that is if L of ft is f of s, means if the Laplace transform of ft is capital Fs, then Laplace transform of e to the at. If I just multiply this ft by e to the at, you don't have to calculate this again. What you can do is, you already have a transform of small f, so you just shift your origin to s minus a. Similarly, if you multiply by e to the minus at, it will shift your origin to minus a. It will add a in your s. As an example, we can see this. So using shifting property, I can write e to the at cosine bt. Is that find the Laplace transform of this one? I know the Laplace transform of cosine bt. That is s over s square minus b square. Right? By multiplying it e to the a, you just need to replace s by s minus a. S by s minus a. So it will be s minus a square, not just s square. Alright? That will be your answer. You got that idea? So if you are interested in finding Laplace transform of, let's say, sine hyperbolic bt, let's say. Alright? What was the Laplace transform? So you need to find this. So let me do it more rigorously. Maybe if you have not understood it completely, then what does this mean is, Sine hyperbolic bt has a Laplace transform of a over s square minus b square. I think this was plus. The inverse Laplace transform of cosine is s square plus b square, right? But hyperbolic has s square minus b square, and this is b over s square minus b square. Now, by multiplying here with e to the at means that shift this thing, you replace s by s minus a. That's the only thing. So therefore, if you add this thing with sine hyperbolic bt s, this will make it b over s minus a square minus b square. Alright, so this will be your Laplace. So that's how we can use the shifting property. It's not difficult, it's very easy. Yeah, there was one more example written at the end, was cosine at multiplied by cosine bt. Now, we haven't heard of anything like this, right? So all I know is I can take one of them. All I know is that Laplace of cosine bt is known to me, that this is s over s square plus b square. Now what to do with this one? But all of a sudden it comes in our mind that this cosine at is nothing but the real part of e to the iota at, right? And cos bt s. Now we know the transform of cos bt. By multiplying with a minus e to the iota t, we are doing nothing but replacing s by s minus iota a. S by s minus iota a plus bc. So now I can left this for you guys to separate the real part. Will you be able to do that? It's not difficult at all, right? Just open this square and multiply and divide by the conjugate of the denominator, simplify it. The terms without iota, you have to write something times iota something. So this is your answer, this part, real part, right? This is the real part. So whatever you will get, the real part is this one. All right? So that will be your answer. You can complete it. I gave you the idea, you can complete. All right? All right, then we have the formula for multiplication by power of t. If Laplace transform of ft is equal to f of s, then Laplace transform of t n ft is equal to, like if you multiply your function by t to the power, not with exponential. Exponential only shift the origin. What t to the n does is, this will differentiate your Laplace transform n times. If you multiply it by t, it will differentiate it once. T square, differentiate it twice, and so on. And plus and minus sign will change according to the order of the derivative. So here what I have to do is, Laplace transform of t square e to the at will be second derivative of the Laplace transform of et. What is the Laplace transform of e to the at? It is 1 over s minus a. So take the two derivatives of s minus a. It will be minus 1 over s minus a square, and again plus 2 over s minus a cube. So 2 over s minus a cube will be the Laplace transform of this expression. Similarly, the Laplace transform of sine at is a over s square plus a square. You need to differentiate it once. Why? Because t to the power 1 is being multiplied. So differentiate the Laplace transform of sine once to get the Laplace transform of this whole function. Here you will need to differentiate twice the Laplace transform of cosine. All right? And here you need to differentiate n times the Laplace transform of e to the at. All right? So that's how you can find the Laplace transforms if function is multiplied by t to the power. If you divide by t, if your function is divided by t, you need to integrate your Laplace transform from s to infinity. All right? So as an example, 1 minus cosine t by t. So what you need to do is, you just need to pick the numerator only. Only pick the numerator, 1 minus cos t. What is the Laplace transform of 1 minus cos t? 1 over s minus s over s square plus a square, and integrate it now from s, because it is being divided by t, so this will integrate your Laplace transform. All right, so these are very easy examples, you can easily do them. If Laplace transform of the function is f of s, then what is the Laplace transform of the derivative? This gives you, this definition property gives you Laplace transform which involves derivatives. That it is, if you take the Laplace transform of t and ft, then the answer is being differentiated. But here the question is, if you are taking the Laplace transform of the derivative, then what you will do? All right, then this is the expression. It uses the value of the function at 0. All right, so if you take the Laplace transform of the nth derivative of the function, it is equal to SNFS minus, you will keep decreasing the power of s, you see, Sn, Sn minus 1, Sn minus 2, and so on. And here you start with f0, and then you increase the derivative, f prime 0, f double prime 0, and so on. All right, and you have to stop when there is no s remaining. This property is very useful for the solution of differential equations. You see, if you take the derivative, there is no derivative on the right hand side. So if you take the Laplace transform of the ordinary differential equation, it will convert your equation to algebraic equation. You see, it's very easy. Laplace transform converts your differential equation to algebraic equation, and find the roots. That's very easy. We will be doing that later on, so this will get cleared later on. Similarly, Laplace transform of the periodic function with period t. If ft is a periodic function with period t, then what we do is we take the integral from 0 to t instead of infinity. Instead of infinity, we just integrate it from 0 to t e to the minus st ft dt, and then we divide by 1 minus e to the minus st. This t is capital T, because it should not be a function of small t. It is capital T, 1 minus e to the minus s capital T. So we can do these two examples as well. Obtain the Laplace transform of the periodic sawtooth wave function given by this, t by capital T of period t. So what you will do is you will integrate this t by t with e to the minus st from 0 to capital T and divide by this factor to obtain the Laplace transformation. Similarly here, it is also a periodic function called full wave rectifier function, e to the sine omega t. So you can find the Laplace transform of this thing as well. The last property of Laplace transform is Laplace transform of the Dirac delta function. We discussed this function in detail when we studied the Green's function. All right. So now, what is the Laplace transform of this Dirac delta function? You need to integrate, because you are taking the Laplace transform of delta t minus as. So you need to multiply by e to the minus st. And there is a property of Dirac delta function. Whenever you multiply your Dirac delta function with some function, it picks the value of that function at t is equal to a. So it becomes fa. So here it will happen again, that this Dirac delta function will pick the value of this function at t is equal to a. So e to the minus sa will be your solution. We have not seen yet the answer coming out to be exponential. In all those elementary functions, the answer was never exponential. So here you got the exponential power. So it means the exponential function is the Laplace transform of the Dirac delta function. All right. So let's prove some of these previous things. Let's pick one from each property and solve them. I solved this shifting thing. Let's do one example from these, when t to the power is being multiplied with some function, and then we will go on to this property, one of these examples. This is easy. I don't need to solve it, but we can do it. Here there are a couple of examples, so let's try some examples. all right, for our practice. So first was multiplication by the power of t. So t to the power n ft s is minus 1 to the power n, nth derivative of capital Fs, right? So Laplace transform of t square e to the at s minus 1 to the power n, second derivative with respect to s of Laplace transform of e to the at, your function, right? We need to take the Laplace transform of this function, and this t square will indicate the second derivative. So minus 1 square becomes plus 1, and the second derivative of what is the Laplace transform? It is s minus a. So first derivative is minus 1 over s minus a square, and the second derivative is plus 2 over s minus a cube. So this is your answer. So see, that's how easy it is to find the Laplace transform of some function which is being multiplied by Tn. Another example was Ltn e to the at. So that is minus 1 to the power n, Tn e to the minus at, dn by dsn, Laplace transform of e to the minus at s one over s plus a. So if you integrate 1 over s plus a n times, what you will get? So here you take the nth derivative and get the answer. Another way of doing it is this. Also, I can write this e to the minus at here and tn here. Then you have to take the Laplace transform of tn, then take the Laplace transform of tn only, all right, and shift your origin from s to s plus a, right? Because this says that if exponential is being multiplied by some function, what you can do is you can take the transform of the function and shift the origin, all right? So both, you can use it by shifting property or differentiation property. It's your choice. It was n factorial over s n plus 1. Here s will be shifted to s plus a, so you will get n factorial over s plus a to the power n plus 1. And verify that this will be the same thing here. All right? You should get the same thing here as well. All right. Of course, when you take the derivative, one power increases. So nth derivative will give you s plus a to the power n plus 1. All right. Because first derivative will give you s square, second will give you cube. So nth will give you n plus 1. And of course, every time you will be getting multiplied by 1, then minus 1, then 2, minus 3, 4, minus 5, 6. So plus 1, minus 1, plus 1, minus 1. So you will be getting minus 1 to the power n is outside. You will be getting minus 1 power n factorial over s plus a to the power n plus 1. And now this minus 1 power n and minus 1 power n, it will become minus 1 to the power 2n. 2n is always even, so minus 1 to the power 2n is plus 1. So they'll cancel. All right, so you'll get just n factorial over s plus a to the power n plus 1. So you see, sometimes one problem can be solved by using two different properties. Our next example was Laplace transform of if ft is divided by t, then the Laplace transform, what we do is we don't worry about this divided by t, we just take the Laplace transform of ft, which is fs, and we integrate it from s to infinity. This will take care of this t in the denominator. So as an example, I think I wrote the example over there, 1 minus cos t over t with respect to s. So that will be the integral of Laplace transform of 1 minus cosine t with respect to x with respect to ds. So you need to take the Laplace transform of only 1 minus cos t. This 1 over t thing will convert this to integration. Alright? So what is the Laplace transform of 1? It is 1 over s. And what is the Laplace transform of cos t? It is s over s square plus 1. Alright? So you need to integrate. So now we need to integrate it. What is the integral? 1 over s is log of s minus s square plus 1 has derivative 2s. So if you adjust this 2, then you will get natural log of s square plus 1 as it is. Alright? And this is from s to infinity. So that is log of s over square root of s square plus 1 from s to infinity. So you got two things. You got log of s over s square plus 1 at infinity means limit s goes to infinity, and minus if you take 0 log of if you take s, then it is log of s over s square plus 1. Now here if you take limit goes inside of the log, and it is 1, of course. Limit of inside is 1 because in the numerator the degree of s is 1, in the denominator the degree of s is 1, and their coefficients are 1 as well. So if you divide by s throughout and take the limit, you will get 1, and log of 1 is 0. Right? So your answer is 0 minus, so 0, don't have to write it. So if you want to get rid of this minus 1, you can invert inside thing. You can write s square plus 1 up and s down, and this minus will be compensated. Alright? So that's how we can find the Laplace transform of function using the integral of the Laplace transform. Alright? So this is one example from that property as well. Then we went on to study the Laplace transform of the periodic function, that if ft is periodic with period t, then the Laplace transform will be 0 to capital T e to the minus st ft dt divided by 1 minus e to the minus s capital T. So this is the formula for the periodic functions. Let's see an example. As an example of this function, I wrote the example sawtooth function, that your ft is t by t from 0 to t. So if I take the Laplace transform of this function of period t, I will get 1 over 1 minus e to the minus st, and 0 to t is e to the minus st, and the function is t over capital T dt. This t comes out, and you can integrate by parts. 1 over capital T, 1 minus e to the minus st, this comes out, and you can integrate this by parts t and st. T as it is, e to the minus st by t from 0 to t minus 0 to t. T derivative of t is 1, and it is e to the minus st dt. Alright. So at capital T, e to the minus st by minus s, right? That will be the integral of this thing. So if you replace t, you will get capital T e to the minus s capital T. This outside thing is the same. So capital T e to the minus s t over minus s, and 0 will make it 0 because t is being multiplied, so 0 will make it 0, plus 1 over s outside, and e to the minus st again has integration divided by minus s from 0 to t. So you will get e to the minus s capital T minus 1 over s square, and e to the minus s capital T minus 0 is 1. So this is what you are getting. Alright. So if you upon simplification, you should get this thing. So upon simplification, you should get this thing. This is the Laplace transform of the sawtooth function, all right? And sawtooth क्या होता है? ठीक है, सा के आगे अगर आप वो देखें, आरी के आगे जो दांत होते हैं उसके sawtooth, तो उसी तरह का इसका ग्राफ होता है. अगर आप t by t को 0 से t तक ड्रा करें, so this goes like this. All right, and it comes back because it's periodic, so it will again start from 0. Again it will start from 0. Again it will start from 0, right? So अगर आप वो आरी का ब्लेड देखें तो उसके आगे इसी तरह के टूथ होते हैं ना, ठीक है? तो इसलिए इसको sawtooth फंक्शन कहा जाता है कि इसके आगे जो नोक वो इसी तरह की नोक्स बन रही होती हैं, ठीक है? This is your function, sawtooth function. All right. So what we studied today is, let's summarize it. We started with the definition of Laplace transformation. We defined it as an integration. It is an integral transform, and then we went on to find out the integral transform of some elementary functions. Almost all the elementary functions we had obtained the Laplace transform of, and then we went on to study the properties of Laplace transform, and we saw examples how to use these properties. All right, so this is a very important topic, Laplace transformation. You might have studied it before as well in different courses, because it's been used in many different courses. So if you have not studied it, it's not a problem. I am doing it very rigorously, as you have seen in today's lecture. So we will keep doing the same topic in Laplace transformation, and we will go further beyond with the same topic. So till then, thank you so much for being with me for today's lecture, and I'll see you in the next lecture. Till then, Allah Hafiz. Assalamu alaikum.